So hello, everyone. And I want to thank you and the other organizers for having put together this nice group of researchers and for having invited me to give a talk here. So I am not a finite model theoretic researcher, but I wanted to show you this work which relies, well, not in finite model theory, but in finite models and on how to encode somehow in the pure syntax of a logic the idea of having finite models to show a negative result again on undecidability and recursively enumerability of a logic, which is, I believe it falls in the interest of most of you. And well, this will be about a particular logic, which is, the modal extension of some many-valued modal logics. So let me start by giving you a brief introduction on a very naive idea. What are these many-valued modal logics I will be speaking about? So the natural idea is to expand many-valued or fuzzy logics with modal-like operators like necessity and possibility and so on. And of course, this comes motivated both from the purely mathematical point of view and also from computer science, and in particular from the area of modeling problems in computer science, because fuzzy logics have long been used to model graded questions there. And modalities like necessity, as I said, but also temporal things, deontic ideas like beliefs and so on, are also rather used in computer science and agent theory and so on. So putting the two things together seem rather natural. And the approach we will follow here is basically the one motivated by this second idea, and will be kind of defining the logics from their semantics somehow. So taking Kripke models, which are basically relational structures, and then enriching them with valuations over algebras, which of course will be algebras arising from many-valued logics in this case. And this approach is based on the Mosowski-Hayek style for first-order logics, which is again similar in the sense that first-order many-valued logics in this sense are defined by taking first-order relational structures and then evaluating variables and relations inside richer algebras. So I say that these modal logics are based on this kind of first-order logics because, of course, we can see them as a strict fragment of them by a syntactic translation. So the systematic study of these logics is under development since they were born as such in the early 90s, and it's still rather under development. Even if there have been a lot of works, they are rather hard to tackle because, at least for now, most of the approaches have been rather ad hoc. We don't have general methods to study them in general. And for instance, already with the axiomatization of these logics, there have been several problems. Some of them have been axiomatized. We will see this in a second, but most of them have not. And in order to study what I will talk about here, about decidability of these logics or complexity, well, it's rather hard because since we don't have finite axiomatizations on the one side, and in general, these logics do not enjoy the finite model property, at least with respect to these semantics I told you about, it's rather difficult to see how can we tackle the decidability question. So what's the state of the art for what concerns fuzzy logics expanded with modalities? Well, for what concerns positive results, we have on the one hand that local modal getter logics are decidable, and this was proven by Javier Caicedo and George Metcalfe and others. Even if it's rather easy to see that these getter modal logics do not enjoy the finite model property with respect to these usual semantics based on Kripke models. So they, Javier and George, developed an alternative semantics, but this semantics is, well, it's more convoluted in some senses, and is not adaptable, at least not naturally adaptable to other logics. So they show that the logic with respect to that semantics enjoys the finite model property, and that's how we can see the decidability. But of course, it's again rather ad hoc. It's very dependent on the characteristics of the Gödel logic. On the other hand, theorems and also, well, local entailment of Lukasiewicz modal logic for models where the underlying Kripke frame is crisp, let's say, is classical. So the accessibility relation is not valued over the algebra, but just 0 or 1. We can see that they are decidable via certain results by Hayek for the analogous first order logic. And this is fairly fast to see. On the other hand, this is all for what concerns positive results. And on the bad side, well, let's say bad side, we have that, for instance, already for Lukasiewicz, well, the Lukasiewicz modal logics have not been axiomatized, and we only have an axiomatization, if we can, well, we will call it like this, for the infinitary version of these logics. So this was done by Bruno de Heu in his PhD thesis, and the drawback is that it has an infinitary inference rule. So it has a rule with infinitary many premises, and of course we cannot hope to use that kind of axiomatization to tackle decidability or other related questions. And for the product modal logics case, we can say it could be even worse. I was working on this for my PhD, and we could only obtain an axiomatization for the extension of product modal logic, also with rational constants, and only for the infinitary logic again. So again, we have an infinitary inference rule. So this is not so desirable. And we wonder if we could say something else. Can we really tackle what happens with the Lukasiewicz model logic and the product model logic? So we were inspired by some results by Scarpellini and Ragas, who show that first order, well, the set of theorems of Lukasiewicz first order logic arising from the standard Lukasiewicz algebra is not recursively enumerable. But on the one hand, well, modal logic is a strict fragment of the first order logic, so we could not hope to inherit the negative result directly from first order into the modal logics. And on the other hand, the way Scarpellini and Ragas show these negative results in first order, of course, relies on encoding rather complex questions in first order, whose language is much more expressive than the one in modal logic, and we could not hope to translate their proofs. So this served as an inspiration, but not, well, not really as via to work with, but just more like an objective. So let me move to the theoretical basis of the things I'm going to show you, because otherwise we are speaking a bit in the air. And before anything, I want to bring your attention to what I mean by logic and by decidability or computability of a logic. Because for this talk, you need to take into account that I will consider that a logic is a consequence relation. So it's a relation that is reflexive, transitive, and is substitution invariant. And it's not going to be a set of formulas, because as I will show you later, in modal logic, well, we do not enjoy in general the usual deduction theorem, so we cannot move from deductions to set of theorems. And it's very natural to see that there are two logics arising from the usual semantics based on Kripke models, which are not the same, but whose set of theorems is going to be the same. So of course, we need really to consider logics as consequence relations. And then when I say that a logic is decidable, what I mean is that the set of pairs where a formula follows from a finite set of premises is decidable. A logic is recursively enumerable whenever the previous set is so. And something interesting is that Craig's trick that says that a logic is recursively enumerable if and only if it's axiomatizable in the usual sense can be extended to logics in this sense, to logics as consequence relation. And that's why I will be talking about axiomatizability instead of recursively enumerability for what concerns logics, just because it's faster to say and maybe nicer or whatever. So this is something you need to take into account for this talk. So for the non-modal part of these logics, let me briefly introduce to you the most general setting I will be using, and these are FLO algebras, or what I will be calling residuated lattices in this sense, are basically bounded residuated lattices. And I will write that phi follows from a set of premises in a class of residuated lattices if and only if it does so in the one assertional logic arising from that class of algebras. And some well-known cases, which are the ones I will be addressing in this talk, are the standard Lukasiewicz algebra, where the monoidal operation is defined in this way, the product standard algebra, where the monoidal operation is just the product in the real unit interval, and the Gödel standard algebra, where we have that the monoidal operation is just the lattice conjunction. So let me give you two properties, that I will be using in this in the later. So we say that an algebra is n-contractive whenever if we take any element in our algebra and we multiply by itself more than n times, we stay in a to the n. So we cannot fall below a to the n. And on the other hand, we say that A is weakly saturated if for any two elements such that one is below or equal than all the powers of the other for any arbitrary natural number. Then if we multiply them, we stay in the lower one. So we cannot fall below A times B in this way. So on the one hand, if A is n-contractive, we know that A to the n is an idempotent element for any A in the algebra. And on the other hand, if A is weakly saturated, if the infima of B to the n for arbitrary B exists, then it is going to be idempotent too. And these things are kind of important in the details of the proof, even if I won't come to them. But it's interesting to have them in mind. So I will address by this way, which I will be calling non-n-contractive weakly saturated lattices, two classes of weakly saturated subdirectly reducible residuated lattices, such that for any natural number, there is some non-n-contractive algebra in the class. So this is rather horrible, but examples of these, which are the ones that we will be more interested, are the set with just the standard MV algebra, the class of all finite MV algebras, and the set with just the standard product algebra. And things that are not non-n-contractive classes of weakly saturated residuated lattices are the standard Gödel algebra or the variety generated by all MV algebras or the all product algebras. So from here, we expand this propositional semantics with two unary modal operations, box and diamond. We could expand it with just one of them. And in the case of Lukasiewicz, it turns, they both turn to be interdefinable. In the Lukasiewicz case, they do not, but in this talk, I will study the logic with both modal operators. And it is done in a fairly standard way. I will be studying here so-called crisp A-Kripke models, and they are just crisp because what we have is, well, a universe, a crisp or simply classical binary relation, which is going to be the accessibility relation in the universe. And then what we do is to define an evaluation of the variables at each word in the model into our algebra, which is uniquely extended to the full language in the obvious way for what concerns propositional connectives, and for what concerns the new modal operators, they are just an infima and a suprema bounded by the accessible words. And in this sense, this is inherited from first order semantics. And we will say that a model is safe whenever these two infima and suprema are defined in every word, because they could be undefined. I will address by KC the class of safe Kripke models over algebras in K, and by omega KC only the finite ones, so the ones where the universe W is a finite set. And I will abuse a bit notation here and denote by KL and K pi classes of Kripke models valued respectively over the standard Lukasiewicz algebra and over the standard product algebra. And of course, with omega before the finite ones. So the logics that we can define over the previous classes of models are 2, as I said. And this is where this distinction between logics as a set of theorems and logics as consequence relations arise. So if we fix a class of many-valued Kripke models, we have, on the one hand, a possible logic, which is called the global modal logic, which is most similar to the usual way of defining first-order logic. And we say that phi follows from a set of premises if whenever we consider a model in our class, if in the whole model the set of premises is evaluated to 1, then in the whole model the consequence is evaluated to 1 too. But just to take notice, there is also the so-called local modal logic, where truth is point-wise, worldwise, let's say, preserved. And these two logics have the same theorems, but they are not the same logic. So that's why it's important to have this distinction and to understand that the logic in here is going to be not a set of formulas. In particular, because the global modal logic does not enjoy a deduction theorem, so we cannot hope to study just the theorems and understand the logic with that. So let me already introduce the undecidability result. So in full generality, what we were able to see is that if we have a class of non-contractive weakly saturated residuated lattices, both the modal logic arising from Kripke models, safe Kripke models evaluated over the algebras in that class, and the logic arising from the finite models in that class are undecidable. So this is a bit, we say this is not very nice, but in particular, what we get is that the modal logic arising from the global modal logic arising from models evaluated over the standard Lukasiewicz algebra and over the standard product algebra are undecidable. And interestingly enough, the restrictions to classes of finite models are also undecidable. So let me just go a bit into the proof, but not so much. So the undecidability is proven by reducing to the post-correspondent problem, which is given in this way, for the ones of you that are not familiar with it, which is just basically pairs of words, and it's undecidable whether there exists some sequence of these pairs in such a way that if we concatenate the words in the left side of the pairs and on the right side of the pairs, the two things coincide. So the crucial observation is that the monoidal operation of our algebras over non-contractive elements can uniquely express concatenations of numbers like this, because we can somehow plug them as exponents of the variables or of elements of the algebra. And that's what I'm basically using to do the reduction. So just for you to have an idea, if we start from a post-correspondence instance written in this way, what we do is define a set of formulas over 3 variables. So X will be encoding somehow the concatenation of the words in the left side, Y will be encoding the concatenations in the right side, and Z will be an auxiliary variable. And if we have these 3 formulas in this set of, let's say it will be a set of premises, and this last formula in our conclusion, you don't have to really understand all of this. I just wanted to write them down. But what we have is that P is going to be satisfiable if and only phi of P does not follow from gamma P in this global modal logic evaluated over A, and is also going to be happening in a finite model. So, well, the crucial thing is that with this formula, what we can somehow prove is that we can always work with models that will have this structure, so they are kind of linear. And to prove from this theorem, the left to right direction is fairly easy, so we can exploit the non-contractivity of, non-n contractivity for arbitrary n's of elements in our algebra, to be able to build directly one model that is going to be a counter model for this derivation. So the other direction, which is the most hard, most difficult one, but I'm not giving more details than this, will rely on weakly saturation and non-contractivity to prove that indeed we can move from arbitrary counter model to a counter model with this structure, and then use this to translate it back into a solution of our post-correspondence question. So from here, how can we move to non-axiomatizability of these logics? Well, first of all, it's very easy to see that if we have a propositional level and the logic is decidable, then the set of pairs in which we have a set of finite premises and a conclusion, well, not a conclusion, that a formula that does not follow from that set of premises in some finite Kripke model is going to be recursively enumerable, because of course we can somehow enumerate the finite frames, and then we are going to be able for each frame to ask to the propositional logic the right question. And well, this is going to be not so hard to see. What we knew from the previous theorem is that if we have a class of non-contractive weakly saturated residuated lattices, we know that this logic is not decidable. So of course, by basic notions of computability, this logic cannot be recursively enumerable, because if it were, since its complement is also this set is also recursively enumerable, we will have that this logic is going to be decidable. So that's it. This is what I just said. Of course, what this gets us is as a corollary that the logic arising from finite models evaluated over the standard Lukasiewicz and the standard product algebra are not recursively enumerable. But sadly, our logics are not complete with respect to finite models. So how can we proceed from here? Well, in the Lukasiewicz case, we can rely first in a notion that, well, I don't know if Hayek introduced it, it's not so complicated, which is the idea that if we have a model, it's going to be called witness if and only if this, well, the box and diamond, if you remember, were an infima and a suprema. Well, if that infima and suprema are turned to a maximum and a minimum, then since we are working over linearly ordered algebras, we end up having that there is indeed a witness, a successor for each world in which any modal formula takes the value of that formula in that particular successor. And I will address by width of KL, the class of witness Kripke models over the standard Lukasiewicz algebra. So Hayek proved that in first order logic, we have completeness with respect to witness models over the standard algebra. And we can translate that to the modal logic very easily by the means of the usual translation, syntactic translation of modal logic into first order and then back. So what we have is that we can work with witness Kripke models. But the depth of these models might still be infinite. So we need somehow to encode in our logic something saying to us, well, if it's possible, which we'll see it is, something saying that we are not in an infinite depth model. And that's something I think is fairly interesting. That can be done by plugging into the premises of our derivation and into the conclusion of our derivation certain formulas, which are not so different from the ones, at least in the idea, in the heart, from the ones that were used in the undecidability proof. And they are basically saying to us that the model will not be infinite, will not have infinite depth, because what we are doing is having some, well, this is going to be saying to us somehow, well, the two first formulas, they are going to be saying to us that P is going to be a constant along the model, and Q is going to be powers of this P up to the depth of the model. So since we are plugging in the right side, something saying that that P is not going to be 0 or 1, and Q is not going to be 0 or 1, because you always have to think in the counter positive here, then of course, since Lukasiewicz standard algebra is Archimedean, it's going to be saying to us that the model cannot be infinite. So I think this is fairly interesting, that we can encode within the logic the idea that the model is finite. This is what I already said. And finally, since it's decidable, given a finite set of premises and a formula, it's decidable to check whether they have this structure for some PQ. Then what we have is that indeed the finitary companion, so the logic arising from safe Kripke models evaluated with the standard Lukasiewicz algebra, is not axiomatizable, it's not recursively enumerable. So basically, this is going to be all because, well, I was able to prove a similar reduction of the for the product case, but in fact, to see that the product modal logic is not recursively enumerable, we can work much easier by relying on some results by Bass and Hayek and Krejcik and some others from the 98, and use that the standard MV algebra is isomorphic to the standard product algebra if we cut its universe to some element over zero. So we remove the only particular element of the standard product algebra, which is the zero in some sense. The reduction showed in this work is for the propositional, well, it's for the basic algebras, but we can adapt this construction for the modal case, and we indeed can inherit the negative result from the Lukasiewicz modal logic into the product modal logic. So I think this is all. This is, well, in a paper recently published. If you are interested, please, you can have a look at it. And that's all. Thank you very much.